All right, 4.6 is about, we're going to start to look at rational functions. We've pretty much, in the first 5 sections of this chapter, we've pretty much summed up all that we're going to say about polynomials. The last 3 sections are going to be about rational functions. Rational functions are a natural thing to look at in conjunction with polynomials because rational functions are ratios of 2 polynomial functions. What we want to do in 4.7, we're going to talk about graphing these things. But to help us get there, we first have to talk about asymptotes and wholes of rational functions. So that's what we're going to do in this section. So first of all, note that if the polynomials in your numerator and denominator have a factor in common, then the rational function can be reduced. Right? So for example, a simple example here, the numerator can be factored as x plus 1 times x plus 1, and the denominator can be factored as x plus 1 times x minus 1. So the x plus 1's cancel, right? And we're left with x plus 1 over x minus 1, sort of, right? So the graphs, so if we call the original function f of x, and we call the reduced function g of x, then f and g should look the same. However, there is one little detail to take care of. Note, for example, that f of x is undefined when x is negative 1, right? If you plug in negative 1, you're going to get a denominator of 0. G of x, on the other hand, is not undefined when x is negative 1. When x is negative 1, you just get a negative 2 in the denominator, and that's not a problem at all, right? So f of x and g of x are not exactly the same function. They're identical everywhere except for when x is negative 1, because when x is negative 1, f of x is undefined, but g of x is not. So f of x should look like g of x, except that it shouldn't have a function value when x is negative 1. We represent this graphically with an open circle where the function value should be, and we call it a whole. Okay? So if f of x is a rational function p over q, right? P of x and q of x are polynomials. So if p and q have a factor of x minus c in common, then the graph of f of x will have a whole at c, limit as x approaches c of f of x, right? So it has a whole at c. The y value of that whole is going to be the limit that the function is approaching when x approaches the whole, okay? So for example, let's see if the following functions have wholes, and if so, where those wholes are. So in order to figure out if the function has a whole, we should start off by factoring the function if possible. From the numerator here, I can factor out a 3. For the denominator, I think I can do x minus 4, x plus 1. So yeah, sure enough, I've got a whole when x equals negative 1. Now what's the y value, right? So so maybe I'll define a new function f star of x or something. This is going to be the reduced version of f of x. F star of x would just be 3 over x minus 4. And it's got a whole when x is negative 1. F of x has a whole when x is negative 1. So I might want to look at what f star of negative 1 is. Right? That would be 3 over negative 1 minus 4. That's negative 3/5. Okay? So it has a whole. So f has a whole at the point negative 1, negative 3/5. Okay? So yeah. So it has a whole at x equals negative 1. You can see that because the numerator and denominator have x plus 1 in common. And then to find the y value of the whole, you find the limit as x approaches negative 1 of f of x. Well, to find that limit, you would start off, you would first factor and then reduce, and then just plug in negative 1 to the reduced version of the function, which is what we've done here, right? So this is the limit of f of x as x approaches negative 1. It's negative 3/5. So that's where your whole is. Let's do another one. the numerator is going to factor, this is kind of trippy. The numerator is going to factor as x plus 3 times x plus 2, and the denominator is going to factor as x minus 3 times x minus 2. They don't have any, the numerator and denominator don't have any factors in common, so there's no hole. There's no hole here. Okay? So that's that. Okay, so that's how holes work. Now going back to our original example, f of x, x squared plus 2x plus 1 over x squared minus 1, it looks like g of x equals x plus 1 over x minus 1, right? Because if you factor and then cancel common factors, this is what you get. So it looks like g of x, but it has a hole at -1, not at -1, 0. Why did I think -1, 0? Did I make a mistake on the first page or something? Oh, no. No, I'm sorry. I was confusing this with, okay, I was confusing this with example 1a. 1a has a hole at -1, -3/5, but we're not looking at example 1a, we're looking at this example. And yeah, if so it has a hole at -1. If I plug in -1, I get 0 over -2, which is just 0. So yeah, this first example does indeed have a hole at -1, 0. So we know that f looks just like g, except it's going to have a hole at -1, 0. But what does g look like, right? What does the function x plus 1 over x minus 1 look like? Well, if we do some division, right? We could even do some synthetic division, but I'm just going to do the long division. X minus 1 into x plus 1 is going to go in once with 2 left over. So really g of x is 1 plus 2 over x minus 1, right? Because it has a remainder of 2. The divisor is x minus 1. So g of x is 1 plus 2 over x minus 1. Or in other words, we could rewrite this as 2 over x minus 1 plus 1. Or better yet, we could write it as 2 times 1 over x minus 1 plus 1. The reason I'm writing it this way is because it makes it very clear that what we're looking at is a translation of, oh, let's call it, I don't know, g star. I'm liking this star business right now. But it's a translation of the function 1 over x, right? It looks just like 1 over x. But it's been shifted right 1 unit, stretched by a factor of 2, and then shifted up 1 unit. Okay, but otherwise it looks just like 1 over x. Okay, so we can graph g just by shifting. It should also be clear, among other things, that g of x is going to have a vertical asymptote at x equals 1, right? Because we shift the whole thing right 1 unit. So the vertical asymptote that we usually have at 0 is going to be a vertical asymptote at 1 now. It also is going to have a horizontal asymptote at 1, because the horizontal asymptote that we usually have at 0 is going to be shifted up 1 unit. We'll talk about the horizontal asymptote in a second, but it should be pretty clear that the vertical asymptote is at 1, which just so happens to be a 0 of the denominator. And in fact, that's not a coincidence, that's true in general. So if f of x equals p over q, and if x minus c is a factor of q, but not a factor of p, so it's a factor of the denominator, but not a factor of the numerator, then the graph of f will have a vertical asymptote at c. Right? So in other words, if c is a 0 of q, but not p, if c is a 0 of the denominator, but not the numerator, then c is a vertical asymptote. So let's look at a couple more examples, and let's identify any holes and asymptotes. So in this first example, I know just by looking at it that I'm not going to have any holes, because there aren't any factors in the numerator, right, that are going to cancel with factors in the denominator. But I can factor the denominator, I get x plus 3, x minus 3. And since neither of those are going to cancel with anything in the numerator, I know that they're both asymptotes. So I have vertical asymptotes at x equals -3 and x equals +3. Okay? So you get that just by doing the factorization. Now compare that to part B. In part B, the denominator factors as x plus 3 times x minus 3. Well, that's just equal to 1 over x minus 3, so long as x is not equal to negative 3, right? So what does this tell us? It tells us we have a hole when x is negative 3, but a vertical asymptote when x equals positive 3. Okay? In fact, what is our hole? So our hole at x equals negative 3. When x is negative 3, y is going to equal negative 1/6, right? If I plug in negative 3 minus 3 is negative 6, so negative 1/6. So I've got a hole at negative 3, negative 1/6, and a vertical asymptote at x equals positive 3. Okay, do you see the difference? In both cases, the denominator factored as x plus 3 times x minus 3. The difference is that in part B, the x plus 3 canceled with the x plus 3 in the numerator. And so that's a hole. In part B, that becomes a hole. Whereas in part A, it's a vertical asymptote. In both cases, the positive 3 was a vertical asymptote, because in neither case did it cancel with something from the numerator. Okay. All right, so that's how holes and vertical asymptotes work. Okay. So by now we've gathered the following information about the graph of f. It has a hole at negative 1, 0. It has a vertical asymptote at x equals 1. And it looks like g of x equals 2 over x minus 1 plus 1. Okay. Note that g of x also has a horizontal asymptote at y equals 1, which we talked about on the previous page, right? Because you're shifting this whole thing up 1 unit. So the horizontal asymptote that we usually have at 0 is now going to be a horizontal asymptote at 1. Since g of x has a horizontal asymptote at 1, and since f of x looks like g of x must also have a horizontal asymptote at 1. Well, how can we think of horizontal asymptotes in general? In general, we think of horizontal asymptotes in terms of end behavior. If a graph has a horizontal asymptote, then it approaches some finite value as x approaches positive or negative infinity. Okay, to explore this idea a little bit further, let's let p of x be this polynomial and q of x be this polynomial. P of x is going to be a degree n, and q of x is going to be a degree m polynomial. Okay, and let's say that our rational function f of x is p of x over q of x. As we saw in, what section was it? It must have been 4.5, I want to say. So in 4.5, we saw that as x approaches positive or negative infinity, p of x is going to be approximately its first term, and q of x is going to be approximately its first term, so that f of x, our rational function, is just going to be approximately the first term of the numerator divided by the first term of the denominator. Now, if the degree of the numerator, n, is less than the degree of the denominator, m, so if this exponent is less than that exponent, then we can cancel out all of the x's in the numerator, right? And we'll be left with some x's in the denominator. For example, to give you a concrete example, here the degree of the numerator is less than the degree of the denominator. So as x approaches infinity, f of x is going to be approximately 2x squared divided by 3x to the fourth. But the x squared here will cancel an x squared there and leave an x squared in the denominator. So this is really just 2 over 3x squared. Notice that as x gets really large, 2 over 3x squared gets really close to 0, right? As x gets really large, this denominator gets huge, the overall number gets really close to 0. Therefore, or thus, if n is less than m, then f of x is going to go to 0 as x gets really large. And therefore, if n is less than m, then f of x has a horizontal asymptote at 0. So the moral of the story is, if the degree of the numerator is less than the degree of the denominator, you're going to have a horizontal asymptote at 0. Now what happens if the degree of the numerator is greater than the degree of the denominator? Right? So if you've got a situation like this, where the degree of the numerator is greater than that of the denominator. Well, in that case, as x approaches infinity, p of x would equal 3x to the fourth over 2x squared. You can cancel an x squared, and you end up with 3x squared over 2. Note that as x gets larger, so does 3x squared over 2. So, if n is greater than m, f of x will not approach any finite value as x approaches infinity. So if n is greater than m, then f of x has no horizontal asymptote. Okay? So if n is less than m, then there's a horizontal asymptote at 0. If n is greater than m, then there's no horizontal asymptote. What if n equals m? What if they're the same thing? Well, if they're the same thing, then we can cancel off all of the x's. So for example, if you had something like this, okay, then as x approaches infinity, f of x would be approximately 3x squared over 2x squared. The x squareds cancel, you're left with 3 halves. So in that case, we get a horizontal asymptote at y equals 3 halves. So in general, if n equals m, then f of x has a horizontal asymptote at the ratio of the leading coefficients. So the next page has a summary of all of this. Okay, so here's how horizontal asymptotes work. Let's say that you've got this polynomial, right? The leading coefficients are a and b. If the degree of the numerator is less than the degree of the denominator, then there's a horizontal asymptote at 0. If the degree of the numerator equals the degree of the denominator, then there's a horizontal asymptote at a over b, right? At the ratio of the leading coefficients. If the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. Now, there are other kinds of asymptotes, which we're going to talk about in a second. But if the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote at least. So let's practice a little bit. So find the horizontal asymptote, if any. So looking at part A, the degree of the numerator is greater than the degree of the denominator. That tells me right off the bat there's no horizontal asymptote. Looking at part B, the degree of the numerator is less than the degree of the denominator. That tells me that there is a horizontal asymptote at y equals 0. Okay. Looking at part C, the degrees of the numerator and denominator are the same. That tells me there's a horizontal asymptote at the ratio of the leading coefficients. And by the way, 3 over 6 reduces to 1/2. So there's a horizontal asymptote at 1/2. Looking at part D, the degree of the numerator is the same as the degree of the denominator. Just be careful, the numerator is not written in descending form, but if you rewrote it in descending form, then this is what you would have. You can see their degrees are the same, so there's a horizontal asymptote at the ratio of the leading coefficients, which in this case would be -2/3. Okay, so that's how horizontal asymptotes work. Okay, so now let's talk about that last case, when n is greater than m, right? When the degree of the numerator is greater than the degree of the denominator. We know that in that case there's no horizontal asymptote, but that doesn't mean that the graph doesn't have any kind of n behavior. In fact, something really interesting happens in these cases. So to explore this concept further, let's say that f of x is p of x over q of x, and that the degree of p is greater than the degree of q. If this is the case, then we can perform long division on f of x, right? We can do a long division problem. Doing so would yield something like this. We would get a of x plus r of x over q of x, where a, r, and q are all polynomials. R would have a degree less than that of q, and so in that case, r of x over q of x is going to go to 0 as x goes to plus or minus infinity. So as far as the n behavior is concerned, r of x over q of x doesn't really affect the n behavior. What does affect the n behavior is a of x. So as x gets really large, f of x is going to be approximately the same thing as a of x. And so that's why I called it a for asymptote. Okay? So therefore, f of x is going to have a of x as an asymptote. As x gets really large, f of x is going to get closer and closer to just a of x. We call this kind of asymptote an oblique asymptote or a slant asymptote. Okay? So an oblique asymptote could be a straight line, or it could be a parabola or a cubic or anything else, right? So number 4 asks us to find the oblique asymptote of this function. Okay? To do that, first of all, note that it does not have a horizontal asymptote because the degree of the numerator is greater than the degree of the denominator. However, that means that we can perform long division. So performing the long division, we get x squared plus x negative 1 negative 4 plus 1 is negative 3. So we get f of x equals x minus 1 minus 3 over x plus 1. Okay? As x gets really large, this is going to go to 0. So the end behavior of f of x is the end behavior of x minus 1, right? So in other words, there's an oblique asymptote at y equals x minus 1. Okay, so here we have this linear asymptote, this linear oblique asymptote. It should go without saying, right? If the degree of p is greater than the degree of q by exactly 1, then the resulting asymptote is linear. If it's greater than by 2, then the resulting asymptote is quadratic. If the degrees are different by 3, then the asymptote is cubic, and so forth. So you get some really interesting looking pictures, which I might show you. Oh yeah, I am. I'm going to show you in Desmos. So number 5 says, find the oblique asymptote of this thing, then use Desmos to graph f of x together with its oblique asymptote, so that you can become convinced that this really is the oblique asymptote of f. So let's do that. I want to divide x cubed by x minus 1. I can actually use synthetic division for this. Right? X minus 1 would correspond to a 0 of positive 1. And then I have x cubed, 0x squared, 0x, and 0. So f of x is x squared plus x plus 1 plus 1 over x minus 1. So that means its oblique asymptote, right? This thing goes to 0 as x gets really large, so its oblique asymptote is this, right? Its oblique asymptote is y equals x squared plus x plus 1. Let's graph this now in Desmos so we can see what it looks like. Uh-oh. Oh, I gotta open up Desmos. So first of all, let's graph the function f of x equals x cubed over x minus 1. Okay, so look at what we get here. We get this weird function. Oh man, when you zoom out, you see it has a second piece. That's really interesting. If you just look at these branches, this one and then this one, it looks like a parabola, doesn't it? In fact, it's going to look like the parabola y equals its oblique asymptote, x squared plus x plus 1. Ooh, look at that. Right? So if I zoom in, you can see that there is a difference, right? There's a difference between the asymptote and the actual function itself. Okay? But the further out we go, the more similar they become, right? Like if I went way up here, I would have to zoom in a lot before I found a difference. See, you finally start to see a difference after a long time. But yeah, so what that tells us is that in the long run, right, the end behavior of f of x is a lot like y equals x squared plus x plus 1. Whoops. So there you go. Kind of a cool thing, I think. It gives us some indication of what the function is going to look like. Okay. There we have it. So we can summarize everything that we've discovered in this section now as follows. Okay, so we've discovered quite a bit. So let's say that f of x is p of x over q of x. P of x is, ax to the n and so forth. Q of x is bx to the m and so forth. And let's say that c is a real number. Okay, if c is a 0 of both p and q, then f has a hole at c, limit as x approaches c of f. If c is a 0 of q, but not p, then f has a vertical asymptote at x equals c. If c is a 0 of p, but not q, then f has an x-intercept at c0. Okay? If n is less than m, then f has a horizontal asymptote at 0. If n equals m, it has a horizontal asymptote at a over b. If n is greater than m, then it has no horizontal asymptote, but it has an oblique asymptote, which can be found by performing long division. Okay? So in the homework in this section, I'm just going to have you identify holes, asymptotes, right? X-intercepts, all kinds of stuff. Let's practice doing that just on one of these problems. So let's find holes, asymptotes, intercepts of this function right here. Okay, so to do that, I'm going to have to factor. I think I can factor the numerator by grouping. If I group the first two terms together, I can take out an x squared, and I'm left with x plus 1. If I group the second two terms together, I can take out a negative 4, and I'm left with x plus 1. So I can factor out the x plus 1, and then I'm left with x squared minus 4. Oh, that's going to factor even further, isn't it? Meanwhile, the denominator is going to be x minus 4 times x plus 1. So let's see. Factoring one more step, I'm going to have x plus 1, x minus 2, x plus 2, right? That's a difference of squares. And then x minus 4 and x plus 1. So what do I know about this? I know that I've got a hole at negative 1. Okay, in fact, I'm going to say this. Limit as x approaches negative 1 of f of x is going to be limit as x approaches negative 1 of this function with the x plus 1's canceled, right? So it's going to be x minus 2 times x plus 2 divided by x minus 4. Well, that's just going to be negative 1 minus 2 times negative 1 plus 2 divided by negative 1 minus 4. That's negative 3 times 1 over negative 5. That's 3/5. Okay, so I know now. So I've got a hole at negative 1 3/5. Okay, I've got a vertical asymptote at x equals 4. I've got x-intercepts at 2 and negative 2. Right? They're the zeros that come from my numerator, 2 and negative 2. Now, do I have a horizontal asymptote? Well, no, because the degree of the numerator is greater than the degree of the denominator, so there's no horizontal asymptote. But whenever I don't have a horizontal asymptote, I'm going to have an oblique one. So to find my oblique asymptote, I'm going to do some long division. X squared minus 3x minus 4 into x cubed plus x squared minus 4x minus 4. X cubed, I'm going to have to do an x. Subtract, I'm going to get a 4x squared. The 4x's cancel. We can bring down a negative 4. X squared times 4 would be 4x squared. So 4x squared minus 12x minus 16. Okay. So f of x is really x plus 4 plus 12x plus 12 over x squared minus 3x minus 4. Okay, so that tells me that the oblique asymptote, my oblique asymptote, is going to be y equals x plus 4. Right, that's that part, because this goes to 0. So at y equals x plus 4, I have an oblique asymptote. So there are all of my pieces of information that I've been able to get from looking at this function. Let's verify some of these things. I'm curious now. So I want to graph this in Desmos. So I've got x cubed plus x squared minus 4x minus 4 divided by x squared minus 3x minus 4. Okay, so check that out, right? So that's kind of a crazy looking function. But look at, so I said that the oblique asymptote would be y equals x plus 4, right? And sure enough, right? So look at that, right? That's the oblique asymptote. We said that we would have a vertical asymptote at x equals 4. Yep, sure enough, we've got this vertical asymptote, this oblique asymptote. We said we would have x-intercepts at 2, 0 and at negative 2, 0. Well, let's see. Yeah, I think so. Negative 2, 0 and positive 2, 0. All right, so those are our x-intercepts. We said we would have a hole at negative 1, 3/5. Ooh, okay, let's see. Negative 1, 3/5. Yep. It doesn't give you the y value, but it does tell you negative 1 undefined, and notice that it changes the circle to an open circle. I wish that it would plot these things, but it doesn't. But anyway, so yeah. So all of our information is looking good, I think. Okay. So that's all I have to say about holes, asymptotes, and intercepts of rational functions. We will graph these things in 4.7.